again, and today we're going to learn about lesson 9.2 about rational and irrational numbers. Let's start. Rational numbers. You already know about decimals and how they are used to write down numbers that are not whole. Some of these numbers can be expressed as fractions. For example, 0.5, which is a half, 2.5, which is 5 halves, 0.125, which is 1/8, and 0.33333, which if we keep repeating forever, are a third, and so on. Any number that can be expressed as a fraction in its lowest terms is known as a rational number. Notice that there are two types of rational number: terminating decimals, with those with a decimal part that doesn't continue forever, and recurring decimals. The decimal part continues forever but repeats itself at regular intervals. Recurring decimals can be expressed using a dot above the repeating digits. So 0.333, as we saw here, is 0.3 with a dot over it, 0.302, 302, 302, 302, and so on, is 0.302 with a dot over the 3 and 2, because they're the starting and ending numbers. And 0.45454544, so on, is 0.45 with dots over the numbers 4 and 5. Converting recurring decimals to fractions. What can we do with a decimal that continues forever but does repeat? Is this kind of number rational or irrational? As an example, we will look at the number 0.4. We can use algebra to find another way of writing this recurring decimal. Let x equals 0.4 or 0.4444. Then 10x equals 4.4444. We can then subtract x from 10x like this, which gives us 9x, which is 4, and x equals 4 9 because you divide 9 by both sides. Notice that this shows how it is possible to write the recurring decimal 0.4 with a dot over it as a fraction. This means that 0.4 is a rational number. Indeed, all recurring decimals can be written as fractions, and so are rational. Worked example 5. Use algebra to write each of the following as fractions. Simplify your fractions as far as possible. So, write your recurring decimal in algebra. It is easier to see how the algebra works if you write the number at a handful of decimal places. Multiply by 10 so that the recurring digits still line up. You subtract, and then you divide by 9. So you just do that again, but this time you multiply by 100 to make sure that the 2's and 4's started in the correct place after the decimal point, so they line up with each other. And then afterwards you divide both sides by 99, because 100 minus 1 is not equal to 9. No, it's equal to 99. This time we have 3 recurring digits. To make sure that these line up, we multiply by 1,000 so that all the digits move 2 places. Notice that the digits immediately after the decimal point for both x and 1,000x are 9, 3, and 4 in the same order, like this. So here you multiply by 100 so that the recurring digits begin immediately after the decimal point. Then proceed as in the first example, multiplying by a further 10 to move the digits 1 place. And then you subtract and simplify. Exercise 9.5. Copy and complete each of the following by filling in the boxes with the correct number or symbol. So, for here, x equals, so here we get x equals 5/9. And for b, we get x equals 17/99 after we do the calculations. Question 2. Write each of the following recurring decimals as a fraction in its lowest terms. So, each of these as a fraction in its lowest terms are, respectively, 5/9, 1/9, 8/9, 8/33, 61/99, 32/99, 206 333, 233 999, 208 999, 145, 1790, 31 990, and then this is 9,990, 999, which is 10. What? And then this is 500. Wait, what? Oh, we're at this. Okay, 5,000. Right. I don't know. But this is 8/9. This is 8/9. And this is 999, which is equal to 1. Question 3. Write down the numerical value of each of the following. So the numerical value for each of the following equals 0.1, 0.01, 0.001, and 0.000000001. That's a lot of zeros. Comment on your answers to A. What is happening to the answer as the number of the digits subtracted number increases? What is the answer getting closer to? Will it ever get there? Well, it's getting closer to 0. And yes, if you get infinite numbers of 9s, then there's just going to be an infinite numbers of zeros, which is 4 to 1. And infinite just means an infinite 0 point and then an infinite number of zeros. It's basically 0. So yes, it will get there. Question C. Use algebra to express 0.6 and 0.2 as fractions in their simplest form. So 0.6 in its simplest form is 2/3, and 0.2 in its simplest form is 2/9. Express 0.6 plus 0.2 as a recurring decimal. So it's 0.8. You just add these together, 6 and 2. Now use your answers to see this one. To express 0.6 and 0.2 as a fraction in its lowest terms. So 2/3 plus 2/9 is 8/9. Now repeat parts C, D, and E using the recurring decimals 0.4 and 0.5. So then you get 4/9 and 5/9. The total is 0.9 with a dot over it, which is just 1, because 4 plus 5 is 9, 9, and 9/9 is 1. Explain how your findings for part F related to your answers in part A and B. So, it's because that 0.9 with a bunch of 9s, or we can just say our dot over it is basically 1. because 1 minus that number with an infinite amount of 9 equals 0. So that number must be 9. Must be 1. Question 4. Jessica's teacher asked the class to find the largest number that is smaller than 4.5. Jessica's friend Jeevan gives the answer 4.4. Why is Jeevan not correct? So, even if we could state one number that is larger than 4.4 but is smaller than 4.5, then Jeevan is not correct. So, we can state the number 4.41. It's larger than 4.4 and it's smaller than 4.5. So, Jeevan is wrong. Now, Jessica's friend Ryan now suggests that the answer is 4.49999. 9. The reason why Ryan is not correct is because you can just add more and more and more 9s at the end. So Ryan is not correct. Now, Jessica now suggests the answer 4.49. Is Jessica correct? Give full reasons for your answer, including any algebra that helps you to explain. You think that there is a better answer than Jessica's? So, yes, Jessica is correct. And it is because you can't really say a number that is larger than 4.49 with a dot over it, but smaller than 4.5. So if x equals 4.49, then sin x equals 44.9. 9x is 40.5. X equals 40.5 divided by 9, which is 9 halves, which is 4.5. But it's not really quite 4.5 because here, this is not a 5. And no, there is not a better answer than Jessica's. Exercise 9.6. Question 1. Say whether each number is rational or irrational. So the first 4 numbers are rational. The next 2 numbers here are irrational. The next 7 numbers, 1, 2, 3, 4, 5, 6, 7, from G to M are rational again. And the final 3 numbers are irrational. Question 2. Show that the following numbers are rational. So, 6 could be written as 6 ones. 2 and 3 eighths could be written as 19 eighths. 1.12 with 2 dots over it could be written as 37 33rds. 0.8 with a dot over it could be written as 8 ninths. 0.427 could be written as 427 1,000ths, and 3.14 with 2 dots over it could be written as 3.1499. So, question 3. Find a number in the interval -1 is smaller than x is smaller than 3, so that x is rational, x is a real number but not rational, x is an integer, and x is a natural number. So if x is rational, it could be 2. If x is a real number but not rational, it could be the square root of 5. If x is an integer, it could be 2 again. And if it's a natural number, it could be 2 again. Question 4. Which set do you think has more members, the rational numbers or the irrational numbers? Why? Well, I think it's the irrational numbers, because if you pair up all the rational and irrational numbers, there will be some irrational numbers left over. Even if you paired all the rational numbers, there's just more irrational numbers. Question 5. Mathematicians also talk about imaginary numbers. Find out what these are and give one example. So an imaginary number is stated as xi, where x is a real number, any real number, and I equals the square root of -1, which is an imaginary number itself. And one example is I. So, that's the end of this video. Thank you and goodbye.